Okay, good morning children. As you know, we had done structure isomerism, we have done, and another part of isomerism is stereoisomerism that we are going to discuss today. Stereoisomerism are of two types, geometrical and optical. So what are they? Geometrical isomerism happens for alkenes. Uh, alkenes, not only alkenes, it can be with some other compounds also, but there has to be carbon-carbon double bond. Carbon-carbon double bond in it, then geometrical isomerism may arise. Say simple. So first of all, what is geometrical isomerism? Suppose we have this group attached. This group attached. So this is a compound, and you see another compound. If we have like this, here just see the placement of this group. Here it is B. Here it is A. Now here, if I make it the other way around, suppose A here and B here. Here it is B and A, here it is A and B. So the arrangement is different, and you know, because of this arrangement, these two compounds will have different property. These two are different compounds, and they are said to be geometrical isomer. They are geometrical isomer, and when same groups are on the same side of double bond, then it is called cis isomer. When same group is on the opposite side of double bond, it is called trans isomer. And this geometrical isomerism cannot happen with carbon-carbon single bond. It doesn't happen with carbon-carbon triple bond also. That you should try to find out the reason for that. It happens only in case of carbon-carbon double bond. It happens with carbon-carbon double bond because, you know, carbon-carbon double bond, it is sp2 hybridized. This molecule is planar. This is planar. And when same groups are on the same side of double bond, it is called cis. When same groups are on the opposite side of double bond, it is called trans. Okay, now why there occurs these two forms? Because, you know, here since there is double bond which is made up of a sigma bond and pi bond, you know, carbon-carbon sigma bond, you know, has free rotation, but when there is a carbon-carbon double bond, then free rotation is not there. And as a result of that, you know, there will be geometrical isomerism. Like this group is A, it cannot rotate, but you know, if it is single bond, there can be rotation. There can be free rotation of carbon-carbon single bond, and carbon-carbon double bond, that free rotation is not there, and because of that rotation is not there, there can be two forms of geometrical isomerism. Geometrical isomer, one is cis and another is trans. Now suppose say this compound C2H2 Cl2. Suppose C2H2Cl2, you are asked to draw their geometrical isomers. So answer will be like this. So suppose I am rubbing this one here. So since we have two hydrogen, suppose one hydrogen is here and the hydrogen is here. So you see, I'm making the cis one, chlorine here, chlorine here. So this is cis form of this compound, and trans form of this compound is here H, here Cl, and here H, and here Cl. So this compound exists in two geometrical forms, cis and trans. Now suppose if I ask to name this compound, this compound will be name of this compound will be cis 1, 2 dichloro but. No, not but, there are two carbon atoms, dichloro ethene. This is cis 1, 2 dichloroethene. This one will be trans 1, 2 dichloroethene. Now, you should know condition for geometrical isomerism. Okay, condition. There is certain condition is required for geometrical isomerism to take place. In fact, there are two conditions. First condition is that there should be carbon-carbon double bond. There should be carbon-carbon double bond. Presence of carbon-carbon double bond is required. First condition. And second condition is each of doubly bonded carbon, must have two different groups. Each of doubly bonded carbon must have two different groups. Like here you see, here one is Cl, one is H. So two different. Here also you see it is two different. If it is not so, then geometrical isomerism will not take place. For example, here suppose this compound, here it is different, but here it is not different. Then geometrical isomerism will not take place here. Okay. So for geometrical isomerism to take place, each of the carbon atom must be attached to two different groups. That you should remember. And as far as property of these two isomers is concerned, let me tell you is that cis compounds are polar in nature, or cis compounds are polar, and trans compounds are non-polar. Trans compound are non-polar, and because it is polar, it will have stronger dipole forces. That's why cis compound will have higher boiling point, and the trans compound will have lower boiling point. So this much is enough for geometrical isomerism. Now coming to optical isomerism, coming to the case of optical isomerism. Now suppose we have this compound CH4. CH4 is methane, and we know that it has got 4 bonds, and the 4 hydrogens are at 4 corners of a tetrahedron, and it is like this. and you know it is three dimensional, so we can represent the three dimensional nature with the help of dash and wedge representation. Say here we have this one. So this is the dash and wedge representation, and you know if I complete the geometry, then it is a tetrahedron. It is a tetrahedron. You know this carbon is sp3 hybridized. Bond angle is 109 degree 28 minutes or 109.5 degree. Okay. Now. Now, let me, before I go discuss further about stereoisomerism, about optical isomerism, let me talk about some plane mirror and image formation by a plane mirror. You know, say this object O, you know, the image will be like this. And if I bring it, put it over it, then they will coincide. But if we take this object L, you know, image of this will be like this, and it will not coincide. If I bring it and put it over it, it will not coincide. Same, suppose this object M, image will be like this, and if I bring it here, it will coincide. Say this letter N, image will be like this, and if I bring it over it here, it will not coincide. Now, when it coincides, it is called super impossible. When it doesn't coincide, it is called non super impossible. So this is again super impossible. This is non super impossible. So this idea you must have. Now suppose this molecule and suppose this is a plane mirror. Now here all the groups attached are same. Now you know if the mirror image, you see this is a three-dimensional object. First of all, this three-dimensional object, it means that like here this means that I had discussed this H atom, this carbon is on the plane of the board. This H atom is below the plane of the board, and this H atom is towards us in front of the plane of the board. Okay, and you know its mirror image will be such that it will superimpose. Now let us consider a object, you know, where we have four different groups attached here. Four different groups. Say one is H, say another is say OH, another is say Cl, and say another is still another group, say NH2. So a carbon atom is attached to four different groups. Now you know now what it is found is that this compound and its mirror image will not superimpose. And so here in this case we will have this case non-superimposable. And why it is not getting superimposed? We can think in this way because there are 4 different groups attached to it. When 4 different groups are attached to carbon, we represent this carbon by asterisk, and this carbon is called chiral carbon. If a carbon atom is attached to 4 different groups, then it is called chiral carbon. And if chiral carbon is there in an organic compound, then the molecule and its mirror image will be non-superimposable. And when will a molecule and its mirror image be non-superimposable? It will be so when it has a chiral carbon. When it will be having a chiral carbon, if it has 4 groups, all different, then it will be a chiral carbon. Suppose a compound is there where we have here H. So it is no longer a chiral carbon. Its mirror image will be no longer non-superimposable. Okay, its mirror image will superimpose. So this is not a chiral carbon. So so when we have an organic compound and carbon is a chiral carbon, then that compound will be optically active. That compound will be optically active. When will an organic compound be optically active? When it has a chiral carbon. When it has a chiral carbon, when it has 4 different groups attached to it. Now, such a optically active compound, there is an instrument called polarimeter, and if we take this compound inside the polarimeter, there is a small cavity where this compound can be placed, and then what happens is that we pass through that compound a light which is called this type of light plain polarized light. If we pass plain polarized light through this compound kept in a cavity inside a polarimeter, okay, then what will happen is if we have to see it through a portion, we have to see it with one eye, then we will see that the plain polarized light gets deflected, and if there occurs deflection, then we say that the compound is optically active. If when we pass plain polarized light nothing happens, then we say that the compound is optically inactive. And when it will be optically active, when there occurs deflection of the plain polarized light, when there will be deflection of the plain polarized light, when there are 4 different groups attached to the carbon atom. So such compounds, what will happen is there will be 2 forms that I am drawing it here. So you see, this compound having chiral carbon, its mirror image will be this one. This mirror image is this one, and as already said, this image or this molecule and this one, will not superimpose. So they are non super impossible. They are non superimpossible, and then there will occur that isomerism, that is optical isomerism. And we say that these two compounds are optical isomers. These two compounds are optical isomers, and one isomer is called dextrorotatory, and the other one will be called as levorotatory. This is also represented as D form. In short, this is written as L form. In short, is another way to represent. D form is represented by plus, L form is represented by minus. So these two compounds are called optical isomers. Dextrorotatory compound, when taken in the cavity inside the instrument called polarimeter, and when we pass plane polarized light, this compound rotates the plane polarized light in the clockwise direction, in the right direction, and this compound rotates the plane polarized light in the anti-clockwise direction, in the left direction. So these two are, so dextro and levorotatory are the optical isomers. So when will optical isomerism take place? It will happen if there is a carbon atom in the compound which is attached to 4 different groups. That means if there is a chiral carbon present. Now suppose this compound, this property cannot show. This is optically inactive. Say CH3Cl, it is also optically inactive. It will not show optical isomerism. Say CH2Cl2, it will also not show optical isomerism. Say this compound CHClOH and NH2, like this compound only. Here we have 4 different groups. This compound will be optically active. So children, then this is about your isomerism. Isomerism is a very important topic in organic chemistry. We already have discussed in the previous day about structural isomerism. So today what we have done is stereoisomerism. Stereoisomerism means like if stereo means in space, if isomerism happens because of different orientation of the groups in space, then it is called stereoisomerism. So this much for now, children. Have a good day.